Today we'll talk about accelerating IoT, Finserv, and supply chain innovation with JanusGraph and Bigtable. My name is Misha Brukman. I'm a product manager on Google Cloud Bigtable. I'm also a co-founder and member of the technical steering committee for JanusGraph, an open source distributed graph database. And with me today, we have Brian Hull from Expero. Brian.
My name is Brian Hall. I'm with Expero, a consultancy. We've been working with graph databases and doing graph projects for the better part of 5 years. We've been involved with the JanusGraph initiative since its inception, and one of our senior architects is a co-founder with Misha on the committee. It's my hope today that when you're done, you have a good grounding in JanusGraph and why you might get excited and can pick a good use case with which to deploy this technology. What we'll walk through today is a little bit about graph databases for those of you that don't know anything about them yet. We'll talk a little bit about why marrying graph with time series data is a very powerful paradigm. We'll walk through how that manifests itself in a few different use cases in IoT, financial services, and supply chain. And then at the end, Misha will walk you through how you would actually make this happen on GCP. It's important to note that while what we're talking about here today is reasonably new, the mathematical foundations upon which it's built have been around for millennia. The original graph problem was solved by a Swiss mathematician in the 1700s by the name of Leonhard Euler, and he solved a famous intractable problem called the Bridges of Königsberg by reducing it to what is now known as modern graph theory. It turns out that a lot of the same things, the same paradigms and concepts that he used to solve this problem are also useful for solving your tricky Sudoku puzzle, as well as determining the fewest number of moves to swap positions on a chessboard. A little more tangibly, there are several real-world algorithms that can be put to use. Clustering, betweenness, similarity. We all know what PageRank is good for. I would recommend that you look at some of the URLs at the end of the presentation. There's several great recipes on the TinkerPop website with graph algorithms and good use cases as to when to use them. Graphs are modeled in the real world all over the place. Transportation networks can be modeled as graphs. Computer networks and IoT can be modeled as graphs. The canonical social network that we're all familiar with can be modeled in a graph. Interestingly, the first commercial database, IBM's IMS, modeled a graph as a bill of materials in the late 60s for the Saturn V project. When we talk about graph databases, one flavor is known as the RDF Triplestore, stands for Resource Description format, coming out of research around the semantic web in the late 90s. It consists of a three-part tuple with a subject, predicate, and object. In this case, I've got Brian as a person, Misha as a person. Brian knows Misha. These are all examples of RDF triples. Sparkle is the query language, and this is not what JanusGraph is. So the second category of graph database is something called a property graph, where you have both vertices and edges. Each of them may have properties, and edges are directed. While Sparkle is the lingua franca for RDF triples, there are various query languages to be used against property graphs. JanusGraph is a property graph, and the query language that we use here is something called Gremlin. When we work with clients all over the place, we try to pick the right use case and ask them, is the graph a good fit for this use case? So usually it consists of a couple different questions. Are there natural networks in my data? And do I have to traverse the graph in order to get the answers to the questions I'm asking? Oftentimes we work with clients and the answer to the first question is yes, and the answer to the second question is no. For instance, in a supply chain use case, I might think that graph would be a good application if I, for instance, was looking to see an outage and how it might ripple through my supply chain. But conversely, if I'm trying to figure out what is the net sum total of widgets in my suite of warehouses? That's kind of a classic SQL use case. So it's always important to make sure that you pick the right use cases and the right problems when you deploy this technology. But when you do find the right problem, it can be a very concise and elegant solution to the questions you're asking. This example here is a dirt simple recommendation engine where on the left you see a 14 table inner and outer join, and on the right you see a very concise Gremlin query. This is actually built under the premise that if you and I have 9 of the same products in common and I have the 10th one, you're likely to also want that 10th one. What we also find in many cases is marrying a graph database with a time series data can be a very powerful paradigm. What we end up modeling frequently are atomic unit snapshots in time where I'm capturing a stock price on a given day or a reading on an IoT sensor. And then as I stack them together, then I've got a time series. So this gives me the micro view of what is happening at any given point in time and how it trends over time. When I marry that with a graph, what I can also do is get a bigger sense of how these things are interrelated and possibly understand causality. Why is this thing trending up while the other thing is trending down? If I see either of them on their own, I don't have that context. If I see it modeled as a graph in conjunction with the time series, then I might be able to understand the relations and possibly even predict where things might go in the future. So how does this manifest itself in use cases in the real world? So for these use cases that we're going to walk through, one in each of the industries, we'll outline the problem. We'll walk through a little bit about how you would model it in a property graph. We'll walk through the use case of how we exploit this data model so that you understand the processing involved. And then in a couple of examples, we'll walk through some user interfaces about how this would manifest itself if you were going to build a finished product. As a reminder, all the things that you're going to see here in a second, these are all property graph models with vertices and edges, and each of them may have properties. Edges are directed. Some of these graphs are a little bit busy, so we've dropped some of the properties just for clarity. So how would I do this in an IoT setting? This model that I'm going to walk through is useful and can be kind of translated in several different scenarios. One would be computer networks. I could model this as sensors in the oil and gas industry, industrial networks, power grids, those sorts of things. So questions we might be able to answer in this setting would be, what does this service actually depend on? You saw the Istio use cases earlier today at the keynote. There's some similarities to what you'll see here. If I'm trying to find the shortest path between 2 nodes in a network, how would I find that? And then the one that we'll walk through here is, what is the impact of a service outage in my SaaS application? So imagine I'm modeling an infrastructure. I've got a SaaS application, and this SaaS application consists of a couple of web interfaces and maybe an external API that my clients are consuming. Each of these, in turn, is reliant on internal APIs, and those APIs are reliant on other internal APIs. At the end of the day, eventually I've got to get data from somewhere, and a couple of these APIs are querying a database, and one of them is querying a search index. So when the system's healthy, everybody's green, but imagine I've got some spike in the CPU on one of my databases, right? I see a time series getting woven into my graph model, and I see the CPU is spiked. Clearly, if that database spikes, then this API is going to be affected. The other upstream API will be affected, and then my web interfaces are going to go out or be in trouble. So while this might be a very obvious, easy to eyeball scenario in a 12-node network, imagine this if you've got hundreds or even thousands of services, and how would I predict what's going to happen based on some outage? That I might use this information in order to deploy limited extra resources. Maybe I've got budget. Where's my biggest point of failure? Where's my susceptibility, or where's my anchor client going to get affected? I might want to put whatever extra budget I have toward making sure that that one is bulletproof. Here's a mock-up generated by us that walks through this use case. You see an Elasticsearch node that's laboring and is affecting JanusGraph and a Spring Boot API going upstream. You see some tabular data on the right and telling us a little bit about what alarm has gone off and why. And down at the bottom here on the next, you see some sort of a time frame. I might want to be zooming forward or back. Maybe I can rewind the clock a little bit and figure out what was it that happened last hour that caused my Elasticsearch node to spike. How might I do this in supply chain? So in supply chain, there are several graphs that can be modeled. In this space, you've got the suppliers and how they interoperate with each other. You've got the actual bill of materials. The finished good, it consists of some raw materials and some subcomponents and subcomponents of subcomponents. You've got transportation networks. How does this actually get from factory to shelf? So questions that we like to ask here are things like, what would happen if, God forbid, there was to shipments if there's an earthquake here today? Where are my bottlenecks in my supplier network? Again, trying to address extra budget. Maybe I can do something to help bulletproof my supply chain. And then for those of us from Texas, what finished products are affected when we have a flood in Houston? So here's a contrived supplier network. Imagine I've got some cars that I'm assembling, and I've got engines and cylinders. I've got blocks, assemblers, and finished products. I've also got a bill of material. In this case, I've got an engine that's composed of a block and a head, and inside of the block, I've got pistons and cylinders. If I put the two together, then what I see is each of the bill of material that may flow through my supply chain. So, turns out, here's your time series again. It turns out each of these suppliers, they have inventory on hand. So I've got some of my engines on the shelf already, and then I want to simulate this disruption. So imagine this supplier down at the bottom is in Houston. Obviously, he goes out. The supply lane actually gets affected, as does that next supplier. This supplier here is affected because, as you see, he's got no inventory on hand in September, right? He cannot weather the storm. Metaphorically. This other supplier, he actually has some inventory on hand, so he's got some capacity to continue to meet his SLAs even after the flood. You also see the bottom supplier, he's feeding into this supplier, so he's unaffected as well. So here you see again where the time series in the graph tells you a better view of the whole. Here's another visual mock-up of supply chain disruption simulator. This is on our website, where you can actually geocode and draw simulated outages based on your supplier network and simulate the effects of an outage and how you might want to try to reroute some of your supplies. How might we do this in a financial services setting? In financial services, you see graph identifying fraudulent activity. You can use the social network model for criminal network detection. And then in this one, we'll walk through evaluating complex structured products. So imagine how would I consider valuing something that's not overly obvious what the current value is. So in the first two examples, we were talking through use cases that might be consumed by a finished product. But in this case, imagine you've got a data scientist who's testing some theses. He's got lots of data, some public, some not so public, and he's trying to figure out, how do I value something based on all of these different data sets that I might not be able to assimilate just yet. So in this case, we're going to value a REIT. For those of you who don't know what a REIT is, It's essentially a real estate investment trust, and what that means is it's a big basket of real estate properties that you value in totality. So in our REIT, we've got two properties. One property is a shopping mall in Oklahoma, and the other one is a water park in Florida. And we noticed that we've been able to model that the shopping mall in Oklahoma actually is managed by a professional property manager and also has two tenants that are in it. We've got some public data about the value of this REIT, and we see that it is trending up. And possibly what I've also got is some not so public data where I've got a way to capture foot traffic. Maybe this note at the bottom is my anchor tenant, and I've now been able to determine that there's some correlation between foot traffic in my anchor tenant and the value of my publicly traded REIT. Maybe if I've tested enough theses, I'm confident enough in that hypothesis that I might be willing to trade ahead of that information. So hopefully you see a couple of different use cases and scenarios where coupling the graph with the time series data is very powerful. And now I'm going to turn it over to Misha. He's going to tell you how this actually can come to life on GCP.
Thank you, Brian. So as we mentioned earlier, JanusGraph is an open source, scalable distributed graph database. It's an Apache licensed project. It's backed by the Linux Foundation. There are a number of users and developers of this project now. It's quite popular and it's growing very quickly. JanusGraph provides a variety of support for different storage backends as well as indexing backends. And here we're going to explore how to use JanusGraph with a Bigtable backend for storage and Elasticsearch for indexing. Brian alluded to this earlier. So there's a project called Apache TinkerPop. And TinkerPop itself is also an Apache licensed open source project, and it provides the framework for open source graph modeling and computation, and it is hosted at the Apache Software Foundation. It also provides the Gremlin query language that is used for querying these property graphs. As Brian mentioned, JanusGraph supports the property graph model, and all the examples that you saw are property graph models. Gremlin is quite a popular querying language for graphs, and it's supported by over 15 popular graph databases. Here's an example of deployment architecture of how you can deploy a scalable graph database on GCP. So there's a solution white paper that we've published at that URL. And what you'll see is that in that solution, JanusGraph is running containerized on GKE together with Elasticsearch. And JanusGraph connects to Elastic for indexing, and it's using Cloud Bigtable as the storage backend. And in front of it, there's a load balancer. So you would run a number of different JanusGraph instances, which themselves are stateless. And your applications would talk to the load balancer and be routed to one of the JanusGraph instances. So what is Cloud Bigtable? Bigtable is a sparse, distributed, persistent, multi-dimensional sorted map. That's the description from the paper that we published in 2006. Let's dive into some of the details behind what this is. So Bigtable is a distributed key multi-value store. So for a single key, you can store many different values. Bigtable is sparse in that if you don't write data in particular number of cells, it does not cost you any storage space. So you can store data in rows that is relevant to them, and you don't need to fill out every single cell with null or placeholder values. Bigtable supports atomic operations, so you can modify any single set of values in a single row in a single transaction, and that will be atomic. Bigtable provides a single index, which is the row key, and the row keys are stored in sorted order. So you have a sorted map. Here you see an illustration of what a subset of a table would be in Bigtable, and the various values here are how you would address them. So there are column families, and inside them are column qualifiers, and the way to address a single cell is with a combination of row, column family, and column qualifier. And that said, the map actually also includes a timestamp dimension. So the full mapping of values in Bigtable is with a row key, a column, which is a combination of column family and an optional qualifier, and a 64-bit timestamp. And the values in Bigtable are uninterpreted byte arrays. So you can store anything from JSON to protocol buffers to snippets of audio or thumbnails or anything that is relevant to your particular use case. Every cell in Bigtable, as I mentioned, has an N64 attached to it. So the way to think about it is that Bigtable is actually a three-dimensional database. Every cell can store a number of different versions, and they do not have to match across the different cells in the same row or different rows. So you can store different versions of the data, which means you can store time series within these cells. So Bigtable comes by default with first-class support for time series. And you can also have an optional garbage collection enabled for this. So you can keep writing data, and older data will automatically expire and be garbage collected and removed for you. Let's talk a bit about how the requests are routed in Bigtable. So clients connect to a single endpoint, which is a combination of load balancing and proxy layer to Bigtable before they're routed to Bigtable server nodes. In the following couple slides, I will remove the load balancing and proxy layer, but keep in mind that it is still there, and clients do not actually directly connect to Bigtable nodes, which means they don't need to do any discovery. They don't need to update anything based on the membership of a given cluster. Clients connect to Bigtable server nodes, but Bigtable itself is actually stateless. The data in Bigtable is actually stored in our distributed file system, which is Colossus, which is the successor to the Google file system. And here you can see the sections of data A, B, C, D, and E, which each of those is a subset of a single Bigtable table. So each one of those stores a sorted subset of the keys in that table. Also note that each Bigtable node owns a number of these data regions, and it has exclusive access to them. So this is what allows Bigtable to provide atomic updates within a single row. So an entire single row is contained in exactly one of those locations, and exactly one Bigtable server node is responsible for managing that data, both from a read and write perspective. So now imagine we have one of the server nodes is getting quite a lot of activity from the clients because it is managing a number of the popular data sets. So it's managing A, B, and C, and so it gets more traffic from the clients than other nodes. What we can easily do is just reassign the ownership of the data from one node to another. Note that there's no data motion taking place because none of the nodes themselves actually store any data locally. They provide support for caching, but there's no durable storage at the Bigtable node server level. The data stays in Colossus. There's no movement regardless of how many gigabytes or terabytes you're storing. And this reassignment is very quick, and the clients don't even notice. And again, they don't need to know that they need to connect to a different server node because their requests are transparently routed to a different server in response to Bigtable behind the scenes, doing the optimization to rebalance the data such that we provide good performance regardless of the scale. Now, given that we're able to easily reassign the data ownership from one node to another, this means that it's quite easy for us to scale the cluster up and down by adding or removing nodes to the cluster and from the cluster. Because again, there's no data stored durably on a Bigtable node, this means they're stateless. And if they're stateless, we can easily move them. So the only thing that they store is a cache of knowing what it is that they're currently responsible for, which we can easily reassign. So this means also that a Bigtable node disappearing means that there is no data loss. So Bigtable has no single point of failure here. If you lose a node, there is no data loss because the data is replicated and stored durably in Colossus. Because the nodes don't talk to each other in Cloud Bigtable, Bigtable provides linear scalability and performance. As you add nodes to a Bigtable cluster to make the cluster larger, you get linear scalability in throughput and performance because the nodes don't do any coordination, because the transactions only happen locally at a single Bigtable server node, which means also we can scale up and down without any downtime, again, because of the dynamic reassignment of the data from one node to another behind the scenes. Today, we're really proud to announce that we're launching replication to general availability. So this means that within a Bigtable instance, you can create more than one Bigtable cluster, and when you write data once to a single location, it will be replicated asynchronously to a different cluster. A single cluster provides strong consistency in reads and writes. Once you switch to a multi-cluster model, it will be eventually consistent across clusters. There are no manual steps that you need to take to ensure data is replicated. It will be done for you automatically and synchronized. There are no repair steps. There are no management. There's literally nothing you need to do other than to say, please add another cluster to this instance. And the use cases that this is quite applicable for are both high availability serving for low latency use cases, as well as for separating analytics from serving use cases such that you don't impact your serving traffic from large-scale analytics. And this is going to be GA as of tomorrow, July 25th. It will increase the SLA from 99.5 to 99.95, and there's zero-touch failover for high availability use cases. As I mentioned, the Bigtable data model supports keys in sorted order, and then there's a bunch of cells that in each row you can store data in. So you have cells, and there's columns, and there's the data there is sorted by column. And so JanusGraph, the way it stores a graph in Bigtable is by storing the vertices as the row keys in Bigtable. And as Brian mentioned, there are properties on both the vertices as well as the edges. And so the properties on the vertices as well as the edges and the properties of the edges are all stored within the row for a single vertex. This makes it really easy and fast to find an arbitrary vertex and then find the edges that are outgoing from that vertex because they're in the row and they're always stored in that row together with the vertex. Brian also mentioned the applicability of time series data to a number of these use cases, from IoT to finance to supply chain. OpenTSDB is a very popular open source time series database that stores millisecond precision time series data, and it scales horizontally to support millions of writes per second. OpenTSDB chose a particular schema to support on Bigtable. And here you can see the row key itself is quite complex. It includes the metric, a timestamp, and key value pairs for the tags. Note that in front of the row key, they added a salt. This is to help distribute the load such that if you have metrics that maybe have similar keys, that you don't hotspot since we're keeping everything in sorted order. And then the data is stored in the different cells of the columns of that row. So now you can see that with the integrations that Bigtable provides for both time series with OpenTSDB and graphs with JanusGraph, we can support the use cases that Brian spoke about earlier in the different industries. So Bigtable provides both of these types of use cases, a fully managed petabyte scale database that scales linearly for increased throughput while also providing low latency because of the sorted nature of keys and the ease of finding the keys. And it's great for the time series and graph use cases that we've discussed. So let's talk about what would it look like to deploy a combined architecture of both time series and graph on GCP with Bigtable. So here you have a sample application that is using both JanusGraph as well as OpenTSDB. OpenTSDB, JanusGraph, and Elastic are all running containerized on Kubernetes. They're both using Bigtable. Obviously, each one of them will have a separate data set encoded in different ways, so they can use different tables, but they can use the same Bigtable instance. We have an application that is providing an API that is talking to JanusGraph, and we have data coming in through PubSub that is being consumed by Dataflow that is both publishing the time series data to OpenTSDB as well as sending requests to the API server. Here's an example of how you would deploy OpenTSDB. We have a similar solution as we talked about earlier for JanusGraph. There's also a simple way of deploying OpenTSDB together with Bigtable using Kubernetes on Google Cloud. And we've open sourced a Helm chart for JanusGraph that makes it really easy to deploy JanusGraph on Kubernetes. This is open source on GitHub, and we will have pointers at the end where you can find it. And our partners at Expero wrote this container graph sample service. That is the application that I spoke about earlier. It's a drop wizard-based demo application. It is also open source on GitHub. And what it does is it's ingesting metrics. That is the data that is coming in to PubSub. And the application that I spoke to about earlier, that is the application that they wrote. That is the container graph service that is contacted by Dataflow and that is talking to JanusGraph. And what this application implements itself is a graph API where you can add and remove containers. You can find upstream and downstream services. You can gather the dependencies, so you can do that graph walk that Brian mentioned earlier. If something happens to a particular node, how can I find the upstream and downstream dependencies? What will be affected? And you can add and remove containers. So this architecture is both a deployment architecture of what you might deploy in Google Cloud, as well as the graph that it will encode upon deployment. So it models itself as a graph. Very meta. So how would you connect to JanusGraph? As we mentioned, JanusGraph works with TinkerPop, and TinkerPop project provides a number of drivers in the different languages, and there are project-supported client libraries in .NET, JavaScript, Java, and Python, as well as third-party supported Scala, Clojure, and Go libraries. When you write queries in the TinkerPop library, the queries themselves are not text. They're very fluent and they're written to the language that you're using. So in this case, in Java, this is what a query would look like. So you get all the benefits of your IDE, of the type checking system, rather than combining together or concatenating strings and then sending them to be processed by the server. In this case, the query that we're showing here is not very graphy. It's not very complicated. This is just for illustration purposes. Many of the queries that you'll see in practice will be more complicated, and there'll be quite a bit more to them. In this case, the query that you'll see here, this is just retrieves a list of running containers. But there's much more you can do with this. A query in graph, so this is Gremlin, this is the graph query language, is actually called a traversal. Internally, it runs a state machine, and there are a bunch of steps to a traversal, and they will fall into one of these 5 categories. So when you see at the bottom here, you have G, which is a graph. You will select vertices. This is a map phase. You will filter to find a specific vertex. You'll find out all the outgoing edges by label, and then you'll select a particular attribute on the outgoing edges. So this will find you all the names of all the people that are known by that person in that first segment. So as you've seen, you can use both graph and time series databases to solve a number of different problems in a number of different industry verticals. This will give you both the micro view as well as the macro view of the situation, allow you to explore the data at a high level through a graph, and then dive deep to understand what is the low-level behavior of the system at the micro level using the time series. And JanusGraph and OpenTSDB provide scalable implementations of both the graph and time series data models, and they can be both scaled as stateless services on top of a scalable database such as Bigtable. As next steps, as Ryan and I mentioned, there are a number of resources that you can take a look at to learn more about both everything that we've talked about, as well as find all the demos that we've mentioned. So first, there's the Cloud Bigtable homepage, where you can learn more about Bigtable. Regarding JanusGraph, the first link there is a solution of how to run JanusGraph with Bigtable. That is the architecture that I showed earlier. There is the Expero demo container graph project that you'll find next. And JanusGraph.org has a number of pointers to both our users and use cases, who is running it, how they're running it, what does it support, what language versions that you might want to use with it. Regarding Gremlin, the graph query language, there's an excellent introduction to the Gremlin language by Kelvin Lawrence. That is the first link there. It's an entire book. It's open source. It's also on GitHub, but you can read it at this URL. It provides an in-depth tutorial that you probably want to take a look at. If you're going to use a property graph, you want to learn Gremlin. And there's also a learning program from our partners at Expero that will also help you understand and learn Gremlin and become a Gremlin expert. There are obviously also forums and mailing lists where if you have complicated questions, you can ask questions about Gremlin. And there's Stack Overflow, very active users on Stack Overflow who are also developers of the Gremlin language. Regarding OpenTSDB, as I mentioned, we have a solution here of how to deploy OpenTSDB on Google Cloud with Bigtable. And there's also a number of visualizations in the gallery that Expero put together that you might want to take a look at.